Hi everyone, my name is Jordan Koh and my project is on the prediction of neutralizing antibodies for the novel coronavirus with machine learning. Coronaviruses are characterized by their crown-like spikes on their surface and contain single-stranded RNA. Since the beginning of the 21st century, there has been three major outbreaks caused by three different coronaviruses. In 2003, SARS-CoV caused the SARS pandemic. In 2012, MERS-CoV caused the MERS outbreak in the Middle East. And recently, in 2019, SARS-CoV-2 caused the COVID-19 pandemic. All three coronavirus infections have led to severe respiratory disease and death all around the world. There are currently no effective therapeutics for coronavirus infections. However, neutralizing antibodies have shown promise as therapeutic agents. Antibodies are a form of natural immune defense that bind to the virus and prevent them from entering host cells. Yet, current lab-based methods for discovering these antibodies are time-consuming and expensive. Hence, machine learning techniques have been gaining popularity for accelerating and complementing these lab-based processes for searching potential antibody candidates. For meaningful prediction, the atomic and structural information of potential antibody sequences have to be accurately encoded. One encoding method is molecular fingerprinting, where each sequence is represented as a bit array, and each bit corresponds to the presence or absence of a specific substructure in the molecule. Another encoding method is graph-based featurization, where molecules are represented as undirected graphs. There are three aims in this project. Firstly, we want to investigate the utility of graph features for discovering potential neutralizing SARS-CoV-2 antibodies. Secondly, we want to evaluate mean and max pooling methods used for generating the graph features. Thirdly, we want to compare the suitability of oversampling techniques, SMOTE and SMOTE-N, for resolving class imbalance. Moving on to materials and methods. The dataset was acquired from the coronavirus antibody database and contained over 3,000 antibodies. Firstly, 310 antibodies that were in complex with the SARS-CoV-2 spike protein were filtered out. Next, the paratope and epitope sequences of the complex were identified by aligning the antigen in the complex with a reference spike protein. In addition, 3 more antibodies with the irregular residues were removed. In total, 307 paratope and epitope sequences along with their neutralization class made up the final dataset. Of the 307 pairs of paratope and epitope sequences, 225 corresponded to the neutralizing class, while 82 corresponded to the non-neutralizing class. In total, there were 4 feature sets created using RDKit. The molecular fingerprint feature set was used as a baseline feature set. The extended connectivity fingerprints was the selected fingerprint type. There were 3 feature sets constructed using graph features. They are mean pooling, max pooling, and combined pooling. There are 37 graph features in total, where each encodes a specific piece of information about each atom in the sequence. There were 7 machine learning models used. For each model, stratified 5-fold cross-validation was repeated 10 times to obtain a total of 50 training rounds. There were 2 oversampling techniques applied. The first was SMOTE, which uses Euclidean distance to determine nearest neighbors, and uses the weighted difference between selected points and their neighbors to create new points. The second technique was SMOTE-N, which uses the value difference metric to determine nearest neighbors, and uses majority voting of feature values from selected points and their neighbors to create new points. Moving on to results. For the baseline ECFP models, accuracy in F1 scores dipped when either SMOTE or SMOTE-N was used. For the mean pooling models, accuracy in F1 scores dipped when SMOTE was used, but maintained and improved when SMOTE-N was used. For the max pooling models, accuracy in F1 scores dipped when either SMOTE or SMOTE-N was used. The drop in performance for tree-based models was significantly smaller than that of other classifiers. For the combined pooling models, change in performance was similar to that of the mean pooling models. Accuracy in F1 scores dipped when SMOTE was used, but maintained and improved when SMOTE-N was used. Feature importance scores were calculated for the combined pooling models. For most models, the top performing features were the mean pooling features. After hyperparameter tuning, confusion matrices were generated for mean pooling models trained using smooth N. They were taken from training rounds which gave the maximum F1 score. The models have high recall. They are good at correctly classifying neutralizing sequences. However, they have low precision. They are poor at correctly classifying non-neutralizing sequences. The best performing models were the mean pooling models trained using smooth N. Their accuracy ranged from 72 to 82%, and the F1 scores ranged from 77 to 84%. To conclude, the project demonstrated the utility of graph features for the discovery of SARS-CoV-2 antibodies. Mean pooling were found to capture sequence information more accurately than max pooling, and smooth N was found to be more compatible with graph features than smooth. However, the graph models were poor at classifying non-neutralizing sequences. For future work, other oversampling techniques in combination with undersampling techniques could be explored as well. Thank you for watching.